So today's topic, as I said, is something we haven't taught to this program before, and that's state minimization. So I'm going to start with a little review of state machines, which I know I've done before, but it's important to bring it into context. Actually, there's an item on there which I've dropped for this week because it got too long. That's implementation of VHDL. We've covered that before. So where we're going to go, we're going to focus particularly on more machines this week. We look at Mealy machines next week. And we're going to look at why and how you might reduce the number of states without changing any of the functionality. Now, finite state machines are to digital electronics what programming is to embedded systems in a way. A bit of a generalization, but reasonably true. So, for example, if you were building some VHDL or Verilog to implement, let's say for argument's sake, an I2C interface, which I've done, believe me, you need a state machine to keep track of the sequence of all the bits. So in the case of I2C, there's a start sequence, there's a 7-bit address, and then there's another bit to tell you if it's read or write. Then there'll be an acknowledge, then there'll be an address, then there'll be an acknowledge. As you can see, there's a whole sequence that builds up. If we have time this term, I actually want to use that as an example, having spent most of my summer holiday working on that one. Okay, so state machines are really central to digital systems of any scale. Okay, so they control the flow of information and you keep track of where you are in often quite complex sequences. We're going to look at very simple sequences for this example today. Even simpler, actually, this just to recap on what a state machine is. Well, if you recall, you've seen this slide before. We would have a block of logic here, and it's got, in this case, it's got a single input R. Internally, you have state. Its outputs are a function of that state. So state is just a number. It's a binary number. And you can encode it any way you like, 0, 1, 2, 3, 4, 5, or you can have another sequence. And that's in itself a discussion, but which we're not going to get into today. So we have the next state logic, where we look at where we are and we decide what our next state will be. The state itself is fed into another function, some combinational logic, to derive the outputs. So from more machine, the output is just the state plugged into some logic, and that gets us our output signals. Okay, so when the input changes, we might change state, or we might not. We might stay where we are, and nothing happens until the edge of a clock. So state logic maintains a state, some number telling us where we are in the sequence. It's clocked, that's what this is here. State doesn't change except on the edge of a clock, and the inputs tell you where you go next. So let's look at a state diagram and explain that. Right, so this is the state diagram. If I've repeated this, I apologize. If I'm repeating, I apologize. We start in state 0. The output for state 0 is a red LED on, and the green and the yellow are off. So the R input tells us what's our next state. We will go to the next state on the next clock edge, not before. So if R is a 1, if you hold the button down, then the next state is still 0. If the button is 0, or the input is 0, then the next state will be a 1 on the next clock edge. And if you look at all of these, they all lead back to 0 if R equals 1, asynchronous reset. All right, output is a function of state, so we take the state encoding as a binary number and put it through some logic, some output logic, to derive the signals for red, yellow, and green lights. Okay, so is there anything anyone wants to ask about that? Hopefully you've all seen this before and have a pretty good idea. So we need to encode these states, and we're going to encode them in binary if we're going to build it ourselves. And you might do it like this. So this is your current state. There are 4 states, so we need 2 bits, 0, 1, 2, and 3. So 0, 1, 2, and 3. And for different inputs, we can then determine what the next output is. So when the input is 0, state 0 will become state 1 on the next clock edge, as shown by the diagram. So if in state 0 and r is 0, then the next state is a 1. But don't forget that this doesn't happen until the next clock edge. So you calculate what the next state is going to be, but it won't have any effect until the next clock edge. Similarly, when r is 1, all states lead to 0. We can work out the logic then for next state 1. It's r bar, s1 bar, s0, or r bar, s1, s0 bar, because they're the 2 ones. And we can do the same for these. And if you look up here, I've written that in a more formal way. So I'm paranoid now. I'm checking I'm still online. I'm not talking to myself for 10 minutes. So that's, again, r bar, s1 bar, s0. So that's what we said here. Notice for next state 2, I was able to simplify. It's r bar, s0 bar. Boolean simplification for combinational logic reduces the number of gates. State minimization reduces the number of states, which subsequently saves us on logic. Okay. So I want now to use a different format to what I've used before. And I've got reason for doing this, as you can imagine. So let's re-look at that same state transition diagram and write it like this. So state, next state, and outputs. Within next state, we look at the 2 inputs. So state S0, state 0, goes to state S1 when r is 0. State S1 goes to state S2 when r is 0. 2 goes to 3. 3 goes back to 0. And now notice I've used labels or names. You can call them what you like, rather than numbers, because we don't need numbers at this point. So when we convert state names into numbers, that's known as encoding. And that's the last step. And there's a whole discussion you can have on that subject as well, which we're not going to do now. All right. So state 0 goes to state 1. Now notice if this one, when you're in state 0 and r equals 1, you go back to state 0. And I've written the word self as a superscript. So when you get one of these up here, one of these loopbacks, I'm going to make a note of that. And there's a reason I've done this, as you can imagine. And we'll see what that is. Okay. So it matters how many states we've got. Why? Because it affects the amount of logic we use. So if this is our storage, we've got our state here and duplicated here. This black arrow and this green one are the same thing, really. Okay, so our current state plugs into some logic and we get some outputs. But we also feed it back into the next state calculation, which is the state, the inputs, that's the next state, but it's ignored until the clock rises. Okay, in which case that then becomes the state. So it's a feedback system. Okay, you've seen that before a few times now. I'm hoping it's fairly clear in your mind. Where it impacts on logic is shown here. So remember, we've got 4 states, so that's binary 0, 0, 0, 1, 1, 0, and 1, 1. Therefore, we need 2 bits. So we need 2 D-type flip-flops to store those bits. So this is our state here. Now we're going to reset this asynchronously on power on. So these will both be 0 at startup. That feeds into this logic and should produce a red. Only this line should go high. The states are fed back into this block of logic. It's just combinational logic. And the input's fed into that. We work out what the next state's going to be. Now that's fed into the inputs of the D-type flip-flops, which, as you probably know, are ignored until the next clock edge. When the clock rises, these values are transferred to the outputs of these and latched, and that's our next state becoming a current state. So that's basically the synthesis of a Moore machine. And we'll look at Mealy machines. It's either next week or the week after, depending if Phil's doing the lecture or not. Right. So with that in mind, let's remember that's the next state. It's ignored until the clock edge. That's the current state. When the clock rises, this next state moves to here and becomes the current one. And D-type flip-flops are memory, and they take up a significant number of gates. Now, each macrocell inside your FPGA will have a number of D-type flip-flops, and when you look at the compilation report, you'll see number of registers used, and that's a kind of indication of how many flip-flops you've used. And you've only got so many of them. Okay, so how many flip-flops do we need? Log base 2 of the number of states. Number of states is 4. Log base 2 of 4 is 2, because 2 to the power of 2 is 4. Ceiling means round up to the nearest integer. So the answer is precisely 2. Right? So log base 2 of 4 is 2. Ceiling of 2 is 2. Let's now have a look at it in more general terms. So when you've got 2 states, we need 1 flip-flop. When you've got 4 states, you need precisely 2 flip-flops. 8 states, you need 3, and 16, you need 4. Now, why have I bothered to tell you that? Well, it's really about whether there's any point in going any further and trying to reduce the number of states. So if you've got 9 states in your design, you need 3.17 flip-flops. In other words, you need 4 flip-flops. Yeah. If you can get rid of just 1 state, get down to 8, we save ourselves a precious D-type flip-flop. Okay. Conversely, if you've got 7 states, you need 3. And you manage to reduce it to 6, you still need 3. So you kind of question the benefit of that. Right. But it's really more these cases where you're just over, maybe a 10 or 9. It'd be nice to try and reduce this design. And you might think, well, how's that possible? How can you simplify a state machine? Well, because it's very easy to add redundant states into a state machine. And there's nothing wrong with doing that when you're designing it. But then you can go in and try and simplify it without changing the functionality. Okay, I'll explain. So, yeah, if we can reduce the number of states from 9 to 8, for example, it's worth the effort. 8 to 7, maybe it's not. Okay, so the whole thing is based on this following observation. Or any number of states that have exactly the same outputs and exactly the same or next states are indistinguishable and so therefore are the same. So why not just use one of them? Now, I've got to qualify something here. The same next states. It's almost that simple. All right, but not quite. So let's start with intuition. So let's look at this, and we can use intuition on this one, which is nice. So look at states P and Q. How do we get there? Well, we could be in state B, and if the input is a 1, we end up in P. Or if we're in state D and the input is 1, we get to state Q. How we get there doesn't really matter. It's where we go and what the outputs are. So P has an output of 1, and so does Q. That's tick box number 1. They've got the same outputs. Tick box number 2, their next states are identical or equivalent. Well, whether it's a 1 or a 0, both lead back to C. So if you're in state D, instead of going here, what if we went here? Well, the output will become a 1, and the next state would be C. Exactly the same as if you go to Q. The output will be a 1, and the next state would be a C. You're in the same part of the sequence, the outputs are identical, it's the same. So through intuition, we can get rid of one of these. Okay, so that's the simplest case. Okay, because P and Q have the same outputs and are guaranteed to end up in the next state, in the same place, they do the same thing. we can get rid of one of them. So that's by inspection. That's fine. Same by intuition. Have a look at this one. Something's changed here. They've both got next state transitions that either go to themselves or to state C. Right? So they don't look quite so obviously the same now. But let's think it through. State D, if you get an input as a 1, will go to Q. Now it's from here that matters, okay? The output is a 1. State B, if the input's a 1, goes to state P. The output is a 1. Now let's consider both combinations of inputs from here on. Okay, so you've either landed in state P or you've landed in state Q. If the input is a 0, you end up back in state C, and the output becomes 0. No different. But what if the input's a 1? You end up back in state P, and the output's a 1, or state Q, and the output's a 1. They look the same. They're exactly the same. So when we say the same next state, to self is considered the same, right? So if P goes to self and C, or C, Q goes to self or C, they are equivalent, which is why I've written self on those state transition diagrams. So less intuitive, but still we can spot it if we know to look for it. Okay, as you can probably gather, there is a formal way of doing this so that we don't miss things. Yeah, so once again, we can eliminate Q because it does exactly the same as P. Its behavior viewed from the outside will be exactly the same, so we don't need Q. So we're down from 6 to 5 states, which you could argue is not that useful, but maybe we can keep going. All right, so that's what I mean by equivalent states. So the outputs are the same, and the next states are the same as well, where we consider to self being the same thing. So let's revise this statement. Two states are considered indistinguishable if they've got really important, they've got the same outputs. And then when you look at the next state transitions for the same inputs, the destinations are equivalent. In other words, they either go to themselves or to a common next state. Now, have a look at this. We'll start with intuition. Looking at D and C, their next states are identical. They both go to E or themselves. Right? So to self is considered the same thing because the output you get as a consequence is unchanged. Or to E is considered the same thing. So D and C, because they have the same outputs and they have equivalent destinations, are considered the same. All right? Outputs are equal. Next states are equivalent. Now, this is where intuition doesn't work so well. If anyone can see the next state I can remove in the next 10 seconds, then write it in the question box. Right? But there is another one. And you can look at this for quite a long time and think, well, where is it? And it isn't so obvious. All right. So by inspection is limited. It's limited in what we can do. Right. Yes, there is more. So let's go through this formally, and I'll try and go through it slowly. Let's look at the state transition diagram. I've drawn it this way that I showed you earlier. So we've got the state here, A, B, C, D, and E. The next state for the two different inputs, 0 or 1, because there's only one input, and the equivalent outputs. So remember, transitions to yourself are considered equivalent. So when you go from B to B, it's a transition to self. When you go from C to C, it's a transition to yourself, as shown by these loops here. There are 3 of them. Yeah. Okay, so that's the first thing that's worth doing, just to make it obvious. Okay. Next up, look for equivalent states. It could be 2, they could be 3, it could be 4, all the same, and only keep one of them. Okay, so you can probably see, well, we know D and C look the same by inspection, and indeed you can see that here too. So C and D, the outputs are the same. When the input is 0, you go to E. When the inputs are 1, they both go to themselves. So self and self are considered equivalent. So they are considered the same. So we can just delete one of them. I chose D because I wanted to. I could have chosen C. Now D no longer exists as a state. It's been replaced by its equivalent, which is C. All right. So we've got rid of D. Now we need to rename any instance of D as C, because D and C are equivalent. D's gone, so make all D's into C's. So the one you delete, you go looking for them. Right? Any more D's? Right, got one there, change it into a C. So that's the next step. So that's just done what was kind of obvious by looking at it. All right, let's update our state diagram. We're down to 4. This is good because I went from 5 to 4. I've just saved myself a D-type flip-flop, and I could stop now. However, being me, I'm curious. Can I? Well, everyone knows I'm curious. Can I get rid of any more? Partly because I just want to simplify things. It's a natural instinct of engineers to do that. So let's delete D forever. Get rid of it. All right. Maybe you can see 2 equivalents in this little mix. Remember, the outputs have to be the same. So if you've got 2 rows with different outputs, forget it. They're never going to be equivalent. How about these 2? A and B. When the inputs are 0, they both go to B. Now that's why I've kept the B there. Right? I put the self in, but it's still a B. All right. So state A goes to B, with the input, and state B goes to B. Both go to state C, both have the same outputs. So in other words, A and B unintuitively are equivalent. All right. So you only need one of them. I choose B. I'm going to cut it out and just keep the A one. And don't forget, where we see B's anywhere, we need to replace that with an A. Like that. All right. So B is gone, A's taken its place. So let's update the state diagram. It's really thinning out. And we're basically done. Right? So I've managed to remove 2 unnecessary states. And as I was about to say, you might look at this and think, nah, that can't be right. How could that be the same? Right? You may not believe me, and I wouldn't blame you. Okay. So look and see what we've achieved from that to that. From 5 down to 3. Doesn't look right, does it? Right, okay. So if this was VHDL, I'd be writing a test bench now. But I'm going to do it the manual way. Let's start with the original. This is the state I'm in. This is the input, and it'll take me to this next state. We then get another input, and it takes me to this next state. So let's follow this through. We're in state A, and the inputs are 0, so we go to B. We're now in state B, and the inputs are 0, so we stay in state B. The inputs now are 1, so we go to state C. The inputs are 1, we stay in state C. Now the inputs are 0, we go to state E. And it doesn't matter what the input is now, we end up back in state A. So let's walk down this path. The inputs are 1, so we go to state D, which is here. Then the inputs are 1, so we stay in state D. And the inputs are 0, we go to E. As soon as you're in state E, you go back to A again. Now remember, output is a direct mapping to state. So where we see a D and a C, we get a 0 in the output, as I've drawn here. Okay. So if we start at state A and that's the input sequence, that's the output sequence, according to the state diagram. All right, let's bring in the new one. Right, exactly the same process. We start in state A. The inputs are 0, so we stay in state A. Same inputs, right? The inputs are 0 again, stay in state A. Inputs are 1, we go to state C. Inputs another 1, we stay in state C, and so forth. Inputs are 0, we go to E, then we always go back to A. Now the inputs are 1, so we go to state C. Now it's the same input sequence, I haven't changed it. Yeah. The inputs are 1 again, we stay in state C. Then the inputs are 0, we go to E, and then we go back to A. So I put exactly the same input sequence in. I've got a different state transition because there are only 3 of them. But let's now fill in the 1s and 0s. So where we see a C, we can write 0s. And you'll see it's exactly the same as the previous output. Therefore, you can see that the state minimization is actually correct. So if it seemed a bit impossible, yeah, it's because it's not obvious. Right? You can't just look at a state machine, particularly a big one, or a multi-partition one in particular, and say, oh, yeah, I can see where I've got redundant states. Sometimes you've got to be a bit more formal. Where are we going to go now? Well, not right now. In the next session, be it next week or the week after, I want to have a look at Mealy machines. The difference in implementation between a Moore and a Mealy, how we convert between the two, and how we might save states by using a Mealy machine instead of a Moore machine.